Hello and welcome back to another video. Now today I wanted to show you one of three 2x2 systems of differential equations. Now obviously there are many different sizes of these systems you can study, but today we're just going to be looking at 2x2 system, and specifically we're going to be looking at the real and distinct eigenvalues case. Now this is definitely the easiest one to compute. That is because it requires the least amount of algebra, and it's usually pretty straightforward once you understand how to find things like eigenvectors and eigenvalues. All right, so I've tried my best to write as much stuff on here as possible so we don't waste too much time on that. Hopefully it's kind of clear that in a 2x2 system there's really only three options. You'll either have two real and distinct eigenvalues, you'll have a complex conjugate, and exactly a complex conjugate. They always come in a pair. Essentially what you can think is we're solving a quadratic, and so this ends up being quite similar to our constant coefficient homogeneous linear differential equations from previously, and then obviously we have the option for repeated. So in some ways you can actually think this is like increasing difficulty, like these ones in the bottom are kind of the hardest. But okay, so let's just look at our case one. So given two real and distinct eigenvalues, we're going to say lambda 1 and lambda 2, along with the corresponding eigenvectors v1 and v2, a general solution looks something like this. So we have x, which is our function, is equal to some arbitrary constant c1 times v1 multiplied by e to the lambda 1t, where lambda is just some constant, plus c2 v2 e to the lambda 2t. Now, hopefully this looks very similar to something you've seen before, right, where we have two constants, and so we have like 2 degrees of freedom. So you would need two initial conditions to have a closed form for that. All right. Now, if you're anything like me, you want to see some practice problems. So what I can actually do here is I'll copy this over, and then we can take a look at a problem I put together. So I'll just paste that up there so you can write that down if you need. Okay, so we're going to find the general solution of we have x prime is equal to some matrix multiplied by x. And this is generally how you're going to find this kind of problem. Maybe there'll be some initial condition, but let's jump right into it. Actually, so in a previous video on this channel, I showed how to find the eigenvalues quickly. I'll link that up above, but let's jump right into it. So first we're going to do is we're going to find the m, and in that case we're doing 3 minus 2, which is 1, so then the mean is just going to be a half, and then in this case the determinant looks to be negative 2, I believe. So we have negative 6 plus 4, so negative 2, nice. So then we're going to say that this is equal to, looks like I'm kind of running out of space here, so I'm going to shift this whole thing over just a little bit. Oops, my bad. Let me just move that part over. Okay. So we have lambda is equal to 1/2. So m plus or minus, we have the square root of 1/4 plus 4/2, because we're doing m squared minus p. Right? Oops. So actually I'm going to change that. I'm going to change that to 8 over 4. Because it's equivalent, essentially, what I'm saying. It's just going to be nicer in this form, right? And that, hopefully you can see, is 9/4. So I'm going to do a little bit of simplification here. I'm going to restate it as lambda is equal to 1/2, right? So in here, we have 9/4, and the square root of that cancels out to 3/2. So we have plus minus 3/2, which now we can say is equal to, so if we subtract 3/2, we have negative 1, or we have 2. So those are our eigenvalues. So that was pretty fast. Now we're going to start finding our eigenvectors. So let's first say we're going to do lambda is equal to negative 1. So now I am doing a couple of things in my head here, but essentially what you want to do is you want to subtract negative 1 from here and negative 1 from here. Since we're subtracting negative 1, much simpler way of thinking it is we're just going to be adding 1. All right. So let's write out our little system. So we have 4, 2, and then negative 2, negative 1. Right? Just to recap what I did, these elements, these elements over here have stayed the same. I added 1 here, and then I added 1 here. All right? Hopefully that seems reasonable. Okay. Now if we look at these two systems, it should be clear that the second row is a is double the first one, and that's something that we kind of expected. So I'm gonna say this new row, we're gonna make this row 1, and let me actually save some more space. I'm gonna say row 1 minus 2 row 2. Okay, so we have 2 minus 1, 0, 0. And we can rewrite this as 2x equals y, and we get the following eigenvector. We're going to get that this is 1, and we'll get that this is 2, right? So y is equal to 2 times x. Very good. Let's move on. Now we have lambda is equal to 2. I'm going to write this out. Okay, so we're going to be subtracting 2 from each. So we have 1, negative 2, and then 2, negative 4. We have a very similar system to last time, right, where the second row is double the first. So I'm just going to move this thing over here. I'm going to say R2 minus 2R1. Then we have 1 minus 2, 0, 0. And we can say that x is equal to 2y. And then we get our eigenvector is going to be something that looks like that. Very good. So we're in a nice spot now. So if we look back at our definition, right, we were searching for 2 eigenvectors and 2 eigenvalues. So we found all this, and pretty much we're just at our general solution now. So I'm going to say now, I'm going to say x of t is equal to c1. And let's begin with our first eigenvalue, or sorry, eigenvalue negative 1. So we're going to say c1 times 1, 2, and that's multiplied by e to the negative t, right? Hopefully that makes sense. And then we're going to say plus c2. We have 2, 1, and we have, that's not very neat. Sorry about that. But yeah, this is pretty much it. Just be careful that you label everything so you don't get your eigenvectors and eigenvalues messed up. That would be unfortunate. And yeah, that's pretty much all there is to it. This ends up being our entire solution. So that hopefully is correct. Double checking my work. That looks pretty good to me. If you see something wrong, feel free to shout out. But that's really what goes into these kinds of problems. Let's take another look at an example. I think that'll definitely be helpful. Maybe something here you might have missed. So same idea. Again, let me actually just copy this one up there so I can maybe just be a little reminder. Might be something that's helpful to you. I'll put that up there. Oops. Hope it's still saved. Nice. Okay. Right. So just like last time, we're going to begin by finding the eigenvectors. I'll move this. Oh no, same thing happened. Just move that over there. Awesome. So we're going to first begin, right? Oops. We're going to say that the mean of the diagonal elements, that's going to be 4, right? We're just taking the average of these two. And then we have that the determinant is just going to be 15. So we're going to say p is equal to 15. So then we have m plus or minus m squared minus p. This one's a lot easier. So we have that lambda is equal to, so this is just going to be 1 in this square root. So we have 3 and 5, right? Because we're subtracting 1 and then we're adding it. Awesome. Now let's find our corresponding eigenvectors for each one of these. So let's begin with lambda is 3. Now we're just subtracting, so we have 2, 4, 0, 0. Okay, very nice. So we kind of cut to the chase there. So all we're going to do now is I'm just going to do this. I'm going to say, oops, that's not what I meant to say. I meant to say 1/2 R1, and this is already completely reduced. So we have 1, 2, 0, 0. And what we're saying here is that x plus 2y is equal to 0, right? So writing that out, we have something like this, right? So I'm going to say -2, 1, right? And a really great way of checking that your work is correct here is pretend now I'm doing matrix vector multiplication, right? When I multiply this vector with this one, I should get 0, right? And the thing is, I can add any constant right out over here and it should still work. And you'll see, right? When I do that, I multiply -2 with 1. I get -2 and then 1 with 2. So that's 2. So -2 plus 2 is 0. So we're in a good spot. That's actually, I guess that's kind of how this whole thing is defined, so that should definitely hold if you did it correctly. Nice. So next we have lambda is equal to 5. We're going to subtract 5 at the top. We get 0, 4, 0, negative 2. I'm going to do 1/4 times row 1. And then I'm going to do row 1 plus 2 row 2. And then this becomes 0, 1. And then this one is going to become just 0, 0, right? And essentially the information I get from here is that y is 0, right? And x can be whatever it wants. So we say that x is just 1, just out of convention. And then y can be, well, y is forced to be 0. Okay, awesome. Right, looking back at our formula, we have everything we need, and we can just pretty much jump into our general solution now. So I'm going to say that x of t is equal to, we have c1 times negative 2, 1, and then we have e to the 3t. I'm actually going to change that because that hardly looks like a 3. So we have e to the 3t. And then we're going to say plus C2, we have 1, 0, and if I remember right, yeah, this is e to the 5t. And that's all there is to these problems, yeah. If you do a handful of these, you'll kind of see the pattern. It's not the worst. It is a little long. You do need to find eigenvectors and eigenvalues. As I've said in the past, really recommend this method for that reason. You can really do everything in just a single line. So that's all for this video. I hope that was helpful. Let me try and put out a another video on the complex conjugate, because that one tends to be a little bit more complicated, and then we can regroup. So thanks again for checking out the video, guys. I really appreciate any comments, concerns you may have, and we'll see you later. Thanks.